Hello everyone. Today we're back to calculate a rather difficult integral, the one from 0 to infinity of absolute value log x to the 3/2 power divided by square root x 1 minus x squared. It's a definite integral calculated using a rather special function. If you've seen the previous video, you'll see that the two methods of solving it are very similar. First, we split the integral into two smaller intervals. Let I sub 1 being the interval from 0 to 1 and I sub 2 being the interval from 1 to infinity. For the second interval, let's consider the transformation x goes to 1 by x, which is a common trick in interval calculus. We get then I2 being the interval from 0 to 1 of x to the half power log x in absolute value to the 3/2 power divided by 1 minus x squared dx. This form is still quite complex, but it's more manageable because now we see that it looks very similar to the interval I sub 1 with this integrand and the same bounds. So we introduce a general interval I of s being the interval from 0 to 1 of x to the s power log x to the 3/2 power divided by 1 minus x squared dx. And now we evaluate this interval knowing that I equals I of a half plus I of negative a half. For that, we can do a series expansion, but one question, which one? We can try with the log x just here. We apply King's property and we have log 1 minus x, which can be expanded, but we get 1 minus x to the s power here, which won't be developed easily because 1 minus x to the something power which is not defined is not very nice to expand. Instead, we have a better solution. Look at the 1 by 1 minus x squared just here. We can expand it using the series expansion of 1 by 1 minus x. We know that 1 by 1 minus x squared equals the sum for k starting at 0 of k times x to the k minus 1, which means our interval I of s equals the interval from 0 to 1 of the sum for k starting at 0 of k times x to the s plus k minus 1 times log x to the 3/2 power dx. We want to switch up here the two operators, which is totally possible because the function we're summing and iterating just here is a bounded function because in 0 it's equal to 0 as well as in 1, and the function is continuous, so this is smaller than some constant k, capital K, which means this operation is totally okay. So I of s equals sum for k starting at 0, k greater or equal than 0 of k times the interval from 0 to 1 of x to the s plus k minus 1 power log x to the 3/2 power. The integrand has only powers of x and log x, which shows that it can be expressed in terms of gamma function. To make it appear, we have to let x being equal to e to the negative t, which means dx equals negative e to the negative t dt. And then we have here I of s equals sum for k starting at 0, k times the integral from 0 to infinity of e to the negative s plus k times t times t to the 3/2 power dt. We can transform this integral using s plus k times t here being equal to x, but we can also use a cheat code for gamma functions. This cheat code is knowing that the integral from 0 to infinity of x to the a minus 1 times e to the negative bt dt equals gamma a divided by b to the 8th power. We apply this rule on our sum and we use the value of gamma at 5/2, which is 3/4 times square root pi. I of s equals the sum for k starting at 0, k times gamma 5/2 divided by s plus k to the 5/2 power, which is the sum for which is 3 square root pi divided by 4 times the sum for k starting at 0 of k divided by s plus k to the 5/2 power. Now we have to deal with this strange sum. For that, we introduce the Hurwitz ZETA function defined this way. Zeta of s alpha equals the sum for k starting at 0 of 1 by s plus k plus alpha to the s power. Our sum can be a bit transformed using the favorite rule of mathematicians I named the +1 - 1 rule, which here will be the plus s minus s rule. Here we can do s plus k minus s, and then you see that this is a fraction and this is another fraction. So we get I of s being 3 square root pi by 4 times the sum for k starting at 0 of 1 by s plus k to the 3/2 power minus s times the sum for k starting at 0 of 1 by s plus k to the 5/2 power, which is 3 square root pi by 4 times zeta of s of 3/2 s minus zeta of 5/2 s, and this zeta stuff is multiplied by s here. Now we use this expression to get the integral we were looking for initially, this one, with this formula. For I of 1/2, it's easy because we can just use this expression. But for I of -1/2, here we run into a challenge. The Hurwitz ZETA function here is not defined for alpha smaller or equal than 0, or here this s parameter. So I of 1/2 doesn't have any sense with this expression. So this is valid only if s equals 1/2. If s equals -1/2, then we have to get back our expression of I of s. This one. Here we get I of s being 3 square root pi by 4 times the sum for k starting at 0 of k by s plus k to the 5/2 power. And here we note that for k equal 0, here this term is just 0, so we can let our sum start at 1 instead of 0. So here we have k starting at 1, and then we transform k goes to k plus 1. So here our sum starts at 0 again, and we have here plus 1 and here plus 1. We use the same plus s minus s rule here, s plus minus s, and we get a new expression for s only if s equals to negative 1/2. I of s equals 3 square root pi by 4 times zeta of 3/2 s plus 1 minus s times zeta 5/2 s plus 1. Now we have an expression for I of s for s being equal to 1/2 and another one for s being equal to negative 1/2. Combining these results, we can get back our integral I, and we get here I equals 3/2 square root pi times zeta of 3/2 1/2. This zeta term is not very good looking, but we can change it a bit using summation manipulations. We express this Hurwitz zeta stuff in terms of Riemann zeta stuff, and we get our final expression. We can prove easily then that zeta 3/2 1/2 equals 2 square root 2 minus 1 times zeta 3/2, which mean our integral I, which is the integral from 0 to infinity of log to the third power n square root divided by square root x 1 minus x squared dx equals 3 square root pi 2 square root 2 minus 1 all divided by 2 times zeta of 3/2. Well, this was hell of an integral, and I hope you enjoyed the video anyway. If the explanation was a bit too fast or a bit too slow, let me know in the comments. Next video will be about a, well, strange integral, not so difficult, but we will calculate it twice using 2 different results, and well, I think you will learn something, I hope, at least. This integral will be the integral from 0 to pi by 2 of log sine theta log sine theta all divided by tangent theta d theta. Until next time, study, learn, and progress.